Today's lecture is going to be quite interesting. We're going to look at some computer simulations. This basically means we're going to do random experiments on a computer. We're going to execute random experiments on a computer. Up to this point, our class has been extremely theoretical. And probability theory happens to be a very applicable subject. Many of you will probably have careers where you have to work with computers and program them and do some kind of probabilistic computations along the way. So it makes a lot of sense to discuss computer simulations. It also helps explain the theory a little bit better when you see random experiments being done. Now, what's the point here? The point is you could analyze random experiments in this theoretical kind of a way, but you could also do them and then see what happens. So if you want to analyze the probability of games involving dice, you could work out the math. Or if you have a game involving several dice and it's some kind of complicated game with complicated rules, maybe the math is not that easy to work out because there's like too many combinations to look at, and you just want to get an estimate to the answer. In this case, it's a good idea to throw dice on a computer, generate millions and billions of results, and then just go through it and see how frequently something happens. That's the basic idea of that. Now, you can, of course, do these games and experiments in the real world, right? You can just buy yourself dice and do the experiments, but the problem is that's very tedious to do, so we rather want the computer to do it for us. So the question becomes, how do you make the computer do the random experiments for you so then you can just look at what happens to be able to draw conclusions from that? And this is all based on something called a random number generator. So we call it RNG, random number generator. What's going to happen is it goes back to what we said. Even though probability theory is based on a sample space, and there's a measure on that sample space and all of that, we usually do not work with the sample space. We map the sample space to the real line by a random variable, and then we work on the real line instead. That makes it more convenient. We bring everything back to the reals. And because this is a real number, this is something that a computer can work with, whereas this is something abstract. So we work with random variables. We have a certain random experiment in mind, and when we introduce a random variable, we're mapping it to the reals, and then this is where the data is going to be generated. Now, what is a random number generator? Basically, what it is that it is a way to generate numbers from the uniform 0-1 distribution. What does that mean? That means that we have a random variable which follows the uniform distribution on the interval from 0 to 1. If you forgot what this means, whenever we talk about the distribution of the random variable, we talk about the probability measure that you get on the real line. And the probability measure that you get on the real line follows the uniform probability measure. What does that mean? It means that the probability density function looks like this. It's 0 here, it's 0 here, and between 0 and 1, it's equal to 1. That would be the probability density function. Now, a computer, what it does is that it does for you the random experiment. It generates for you numbers. After all, a random variable is a mapping. And if the sample space consists of an infinite number or an uncountable number of sample points, it would not be possible to put all of that information on a computer. And even when you map it to the real line and you're getting all of those real numbers, you cannot actually put that in. But what you could do is you can do the random experiment, apply X to it, produce a number, and then do it again, and then do it again, and do it again. And this way you generate a finite list of numbers. So what's going to happen is, basically, this is how it's going to look like. You have your interval from 0 to 1, and when you run the random number generator, it will just produce for you a number between 0 and 1. It will produce for you a random point. When you run the random number generator, again, it produces another point, and then another one, and then another one, and so forth. And it produces these points in a way that they're uniformly distributed. So that's the idea. It's supposed to, like, in actuality, you cannot create an infinite number of points. But if you create a lot of them, then you're getting a fairly reasonable idea of what the random experiment is going to be. So let me show you how this works on a computer. Now, the software I'm going to use, you can really use any software you want, but the software that people typically use with this is R software. It's just called R. People will tell you it's not a programming language. They will say it is a statistical software that happens to have a programming language built into it, a fairly weak programming language. It's not a general purpose language. It's not like C, where you can do anything you want with it. It's made specifically for working with data, probability, statistics, and all of that. That's what it's designed for. And it happens to be free. Also, you do not have to download anything. What you do is you go to a site called POSIT Cloud. So you just search for this in a search engine, and the first result that comes up will take you to the main site. You make yourself a free account. I believe you get a certain amount of hours. I'm not sure. They keep on changing it. I think it's 75 free hours for the month. And then if you want to use it extra, you pay. They keep on changing the price. I think it might be $5 a month. But for the purposes of the class, you're not going to be using it 75 hours a month. You'll use it for a little bit, and that would be enough. And if you have to use it for more, you can either download it or you can log in a different account. But even when I was teaching a class on this, and I was using it several times a week, I still had enough hours not to go overboard. So it's usually enough. So you go in, you log in, you do all of that. I think it's mostly self-explanatory. You create a workspace. I'm not even going to show you how to do that. I'm sure you can figure that out. It's just completely self-explanatory once you navigate through the screen. And once you load it, it's going to take you to a page where you just click New Project. So you're going to click on New Project. You give it a name, and then it takes you to the main screen. And I'm going to switch, and I'm going to show you the main screen and how it looks like. So this is how it's going to look like. And so this is what it is. Mine is, as you can see, larger. I'll zoom out a little bit. So this is the way it looks like. If you've used MATLAB, it looks almost identical to MATLAB. And in fact, a lot of the code in MATLAB can be copy and pasted in almost identical fashion. So that's the way it looks like, except MATLAB is not free, and this is free. So here's the way that this works. This window that you see over here, this is a window where it's kind of like a calculator. You type things in. Generally, you use this window to get an answer. It will produce an answer for you. This is not the window where you do the code. You can, of course, type over here if you want to do something very boring. You can type like 1 + 2, and it shows you the answer of 3. The one here that just kind of just says there's one number in this list. That's all it is. It's only used like if you have a lot of numbers and it goes to the next line, then it's just convenient to navigate yourself where you are. But the answer is 3. If you write square root of 2, it will generate for you numbers, pi plus, pi times square root of 2. So at the moment, it feels like a calculator, not anything very impressive. If you want to clear the screen, there's a broomstick right over here in the upper right corner, and you clear everything. Now, what we're going to use primarily is we're going to click on File, New File, and it appears it actually supports different languages here. There's a C file, a C++ file. Well, I do not have enough space here, but they also have a Python file. We're going to just click on R script. This is the one that we're going to use. And when you click on it, it opens up a window up here, and this is where you do most of your work. Here's how a random number generator will work. You will type, this is the command. You write R for random, unif for uniform. This is random uniform. And then you will indicate how many numbers you want to generate. So let's say we want one number. Now to make it run, to make it do, so here's what you can do. You can type runif1 down here in the console window. And if you do that, then you have to click enter, and it will run it for you down here. And it will generate for you a random number between 0 and 1. Now, if you've done it, you got a different number. That's supposed to happen. It's a random number generator. So all of you who are watching this and are following along, your number is, it has to be different from mine. So this is what we have. Now, you can also execute it in this window up here. So the way you do it is you simply highlight all of the code that you want. You have to make sure you highlight the whole thing, and you click the run button, and it will produce for you a random number. And then you can just repeat this. You can just click on the run button over and over again, and every time you click on it, it keeps on generating for you a random number. So that's a random number generator. Now this is, of course, a little bit annoying to just keep on clicking run all the time. By the way, it's important to select the whole thing. If you select part of it and you click run, as you can see, I selected the word run. Our uni, it does not know what that is. You get the error message. Now, it's annoying to generate a random number one at a time, so it's more convenient to indicate how many numbers you want. Let's say you want 20 numbers. You click run, and it will generate for you a list of 20 numbers at random. And you kind of get to see what the purpose of these are. This just says this is the first number in the list, this number here is the 7th number in the list, and so on. And you can really go overboard with this. You can generate 2,000 random numbers. And here it is. It's not going to show you the whole thing. You can ask it to show more, but it will generate, it will show 1,000. And here's your list. And like, for instance, this number over here is the 689 number in the list. This is 690, things like that. So that's the way that this works. Now, what exactly is a random number generator, and how does this work? So I'm not going to explain to you how random number generators work, because this is not the purpose of this course. That would be a separate course, something on, let's say, statistical computation. But here's basically what a random number generator is supposed to do. So a random number generator, it creates data. So by data, I just mean numbers. And this has to be finite data, because you are, after all, talking about a computer. It creates finite data of numbers from a random variable that produces a number in the interval from 0 to 1 in a uniform way, so evenly spread out throughout the interval. And each number is independent of each other number. Now, we did talk about independence in the previous lecture, but here what we mean is, without being fancy, it would just say that, let's say this is your interval from 0 to 1, and I'm going to cut it down the middle. And I produce, and the first number that gets generated is right over here. If these numbers are being generated in an independent way, it means the next number will have no preference of whether it's on the left or on the right. So maybe the left number is over here, the next number, maybe the next number is there, maybe the next number is over there. If the numbers were generated in the way, like, here's a way how you can even, like, the idea is you want to fill out this line in a way that is evenly spread out, but you want to do it in an independent way. Like, here would be a silly way to evenly fill out that interval. You can kind of do it like this, right? Then you can see that, yes, the numbers are evenly filling out the interval, but it would be silly to think of that as a random experiment, because they just go like this in the line. Like, it's dependent. Once you know where one is, you know exactly where the other one is, and all of that. So that would be kind of silly. You want to do it in an independent way. Now, here's the thing about random number generators. Random number generators are not really random. Let me remind you what the word random means. The word random, it basically means unpredictable. You cannot predict what's going to happen next. When you have a coin and you throw it, if you take a coin, you give it to the next person, it's impossible to predict what the person is going to do. Maybe the person is going to put a lot of force, little force, whatever it is. It's impossible to predict what the person is going to do. And even if you know the person likes to throw the coin really high with a lot of force, it's not going to tell you how it's going to land, right? That's impossible to predict unless it happens. But random number generators can be predicted, and you know exactly what the number is. The reason for this, so they're not really random. So there's a few things. First, random number generators do not produce real numbers. Rather, they produce rational numbers. Right? You have a finite number of digits. A real number, the amount of digits that it has is infinite. That's something that cannot be stored on the computer. So computers only work with rational numbers. You can have 20 digits, and that's a very good approximation for a real number, but a real number really has an infinite number of digits. So first of all, you're not really working. So technically, all of the random variables are discrete. Right? There's a countable number of outcomes you can have. So that's the first thing. But the idea is this is an approximation to something, right? It's an approximation to something that's real. The second thing, and you can say, you can actually put these together, they kind of go together, is that RNG is not really random. Not really random. Yeah, it's not really random. You can even drop the word really. It's not random, and everything is completely determined. And in particular, it means everything is dependent on each other. If everything's completely dependent, like dependence, what the word dependent means in an intuitive way is that if the number comes out to be 3/4, maybe I do not know what the next number is, but I know it has to be somewhere close to 3/4. So I might not have all of the information, but at least I'm getting part of the information. So I'm able to pinpoint it down a little bit. But when everything is completely determined, it's even better than dependent. Everything is just completely deterministic. And the thing here is that computers use algorithms. There is an algorithm to determine RNG. So you therefore should understand that since there's a procedure for how these numbers are being generated, if you know the algorithm, then you know exactly how the sequence of numbers is going to go. And in particular, it means the whole thing is dependent. It's not really independent. And allow me to illustrate by going back to show you again how this works. Now, I'm not going to explain how random number generators work. But what they basically have is they have something called, and by the way, if you want to add commentary, human commentary, so the computer does not read that, you use a, I'm not sure what you call this symbol, but you use that symbol. By introducing that symbol, you can then write, you can see it's in green. It just means the computer will not read it. If you click run, it does not read anything. If you remove it, then the computer will read that, and it gives you an error. So you just put that symbol in front, and it's not going to read anything. So random number generators have a seed. So a seed, it's like you put a plant and then it grows. So they have a seed. What this is these are initial conditions. And then from that point on, everything is completely determined. So here, let me illustrate. So you can set the seed. So let's write set seed. So you're going to plant your random number generator, and you're going to set the seed, and let's set to the number 1. And I'm going to click run. So that means I have set my random number generator with this initial condition. Now, if I was to write RUnif1, you're going to notice all of us get the exact same number. All of us get that number. If we run it again, we get a different number, but we're only getting a different number because it's the next number in the RNG sequence. However, if I go back and I set seed 1, and then I click this, you can see I'm getting the exact same number I had before. So this should illustrate to you that this is not being done in a random way. There's an algorithm that produces this. if you set seed is equal to 2, and here I'm going to highlight both of them, it does not actually mean you get, the 2 does not mean it's the second number in the list. So if that's the way it worked, then you should get 0.37, but you're getting something different. Rather, it means this is the initial condition. That's not the position in the sequence. It's not like it's using the same sequence. You rather are taking a number, the initial condition, and then from that point on, you use that to generate an infinite sequence of numbers. I'm sorry, really a finite, I'm sorry about that, finite sequence of numbers. But that's the way RNG works. Now, you might ask, why is it that when we done this random experiment, not really random, but let's call it a random experiment, why is it that when we done this random experiment in the beginning, why is it that we all got different numbers? So what you do, and I'll go back to the other screen. So what you do, so usually we use a real random experiment to generate the seed. And then the algorithm, the mysterious algorithm that we're not going to describe, and it's there's a lot of math that goes into there's a lot of different methods to generate it. It's actually quite interesting. A lot of them use a lot of number theory, by the way. So the one that they use in our software, that's like one of the fancier ones, they call it the Mersenne twister. Mersenne has to do with Mersenne primes, if you heard of those. It's a Mersenne twister. You have Mersenne primes. Prime numbers are good for this. And let's not go there. People put in a lot of work in trying to get a good random number generator. So here's what we do. We use something that's really random, something that really is random, and that generates the seed. Once the seed has been generated, from that point on, the algorithm takes over and it produces for you that sequence. Now, what is being done to generate the seed? You might say, well, if you can generate the seed in a way that truly is random, why can you not generate all the other ones? So this has to do with the fact that to generate something that truly is random, it is not easy to do. So what the computer does, and this is usually what people do, when you log into the computer, it looks at the time at which you log in. It looks at the date on the calendar, and it uses that. It uses in the calendar. It uses the time on your clock. It uses all of that, and that is used as the seed, right? That's something that truly is random. You have no idea what's going to happen, and it will plant that seed and then use the algorithm for everything else. Because, so here's like one way you can generate numbers in a way that really is random. You can take a coin and you can create heads and tails. You can toss a coin in real life and you generate heads and tails. Heads and tails, you can represent them as ones and zeros. And then you convert this number in binary. So you would write this as 1 over 2 plus 0 over 2 squared plus 0 over 2 cubed plus 1 over 2 to the 4, and so on. So you convert that into binary, and this is now a real, well, okay, it's an approximation to a real number. It really is a rational number. So you could generate a real number by using coin flips. The problem is, in order to get a high degree of accuracy, let's say you want 6 digits, so that's 1 out of a million. So that would be 2 to the power 20. So you have to have this sequence be 20 long. So you would have to toss a coin 20 times just to generate one number. And you can see that it's very impractical to do that in real life, right? Generating things in a way that truly is random is difficult. It's computationally ineffective. So it is reasonable to set the seed by using you as the person to set the seed. Your actions as a human being are really random, and they're being used to plant the seed. But from that point on, the algorithm takes over. So that's the way that it works. So now you might be bothered and you might say, well, if an RNG is not really random, then how are we allowed to use it? So what it's called, so people usually call it a pseudo, a PRNG. It's a pseudo random number generator. And it's not really random. The whole thing is determined, as you can see. And you may therefore wonder, well, why are you allowed to use it? So here's the whole point. A PRNG behaves as if it was really random. That's the whole point. That even though it is not, it mimics what it should be. Okay? And so the math never changes. And so basically, and so the math never changes. So it sort of mimics something that's random, and then you're allowed to use it to analyze the data, and the actual math is okay. Like it's okay, it's safe to use, and it will give you good approximations to something that really that would truly be random. So that's the idea of that. And if you couple it with the fact that the seed is random, that makes it a little bit better. And the other advantage is that this is a PRNG is computationally fast, so it's easy to generate a billion numbers super fast. And this is the other part which is actually important. It's also repeatable. You can repeat the same identical thing all over again. This is very good if you want to share your work with another person. If you want to analyze something together, if you've generated your numbers in a truly random way, it would be impossible to then tell someone else this is what you got, because there's no way to generate those numbers again. But if those numbers were generated by a PRNG, then you can just share the algorithm, the seed, and all of that, and then the person would be able to do it. Now, one thing about PRNGs that I should say is that the numbers eventually repeat in the cycle. So what I mean is, let's say you have 1, 2, 3, and then the next number is 4, 7, 3, and the next number is 6, 2, 1. Eventually, at some point, maybe this is like 1 million numbers, you return back and the whole thing goes again. So that's just the way they're coded. You're often using modular arithmetic, if you're familiar with that. It does use a lot of number theory. And so because the number of remainders is finite, eventually the numbers have to repeat all over again. But I think the Mersenne twister that is used in R, the period until it repeats, it's some abnormally large number. It's like 2 to a bit. So a Mersenne prime, it's a prime of the form 2 to the n minus 1. I'm not sure what they put there, but it's an abnormally large number. It's so large that I don't think the computer can even go through the whole cycle until it repeats. So you want, like, part of a PRNG is that you want its period to be so enormous that you never run the risk of kind of repeating the whole thing all over again. But all of them are coded in the way that they have to repeat all over again. Part of the reason is also because you have a finite number of digits. So whatever the digits you're getting, they have to repeat, and then you're back again to where you are. But anyway, that's basically what a PRNG is, and we need to understand it when you're doing computer simulations. So now I want to show you some other ways to generate some other random numbers. So let's clear the board and go back to the other screen, and I'm going to show you something else. Let me show you two useful commands first. Let's say we generate 100, well, let's make it more. Let's say 500 random numbers. It's going to show you all of this. Not very convenient. It's more convenient to give this a name. So let's set that equal to capital X for the random variable. Now we have to understand that technically, so this is the way you do. You set X is equal to that, and then this is what you see. You do not actually see the numbers. If you want to see the numbers in this window, you would just type X, and you would ask it to display what X is. And it will display all of those numbers for you. So that's like a convenient way to do it. And if you want to extract a number in the list, you would just use square brackets. So you would, let's say you want the 15th number in the list, it will show you what that is. Do not use round brackets, because round brackets are used as a function. This is not really I mean, this is kind of funny. Technically, a random variable is a function, but a computer is unable to do that. It does not actually think of a random variable as a function. It thinks of it as a list. So it's not like you're applying, there's some kind of formula to apply it here. I could not find function X. Technically, a random variable is being evaluated at a sample point in omega. That's the strict mathematical definition. But for a computer, it's just a list of numbers where every number represents one outcome of a random experiment. So if you want to see it, so one thing that you can do is you can tell it to do histogram of X. Let's see if this works. I think it's hist. Yeah, that's the way you do it. You do hist applied to X, and it's going to create for you a histogram. If you do not know what a histogram is, it's just like a bar chart. And it would appear right over here. It's a bar chart. It just shows you, if you were to zoom out, it will look a little bit better. It will show you, as you can see, the numbers range from 0 to 1, and the bars just indicate how frequently, this is the frequency, it just shows you the frequency with how often this happens. And it's fairly evenly spread out, which is the way it's supposed to be. The more numbers you use, the better this is going to look like. So if we go back, and let's say we increase it to 5,000, and we let x be 5,000 numbers for that random variable. So I'm not sure what happened over there. Let me do it again. Probably clicked something by accident. So you have 5,000 numbers, and now if you tell it to do hist of x, if you were to zoom in, it will be a lot flatter now. As you can see, now it's more flatter. So the larger you make that number, the flatter it will become, and this is what we mean by evenly spread out. Now, the other thing I wanted to show you is how you can create a probability density plot. Because this is a histogram. This is not a picture of the probability density function. To get a probability density function, what you basically will have to do is you will have to take every one of these rectangles and calculate how frequently something falls into. You have to convert it sort of to percentages to get the PDF. It's similar, but it's a little bit different. And the way you can get the PDF for that is you will tell it to plot density of x. This is the way you do it. You type density of x, and then you tell it to plot it. And now if you do this, it will give you a picture over here. And I'll zoom out so we see it a little bit better. Now this will look a little bit funny, perhaps, that as you can see, there's a number 0, and then it's not actually 0 over here, and there's a 1, it's not actually 0 over there. The reason for this is because the way this is coded is that if you go back to the bars are a little bit uneven. And so if you just connect the midpoints of the bars, it will be a little bit rough around the edges. And what the part of the program to make the PDF picture look a little bit better, it takes nearby points and it averages them out. So it performs a smoothing operation to make it look like a nicer, smoother type of a picture. So technically it is 0 here and it's 1 over there, but when you average them together and you get the nearby points, it sort of smoothly moves from one to the other. Now, if you were to increase, I know you cannot see this because I'm zoomed out, but if you were to increase, if you go back to the code, instead of using 5,000, if you use 50,000, so I'll do it like this. I think this is the best way to do it. I'm going to zoom in. So let's say we have 50,000, and then I'm going to tell it to plot density of x, like this. If I was to run it, then it will be, you can see it becomes like the uniform distribution as we talked about. As you can see, it's becoming flatter. And you can increase that number to 500,000. You can see it looks even flatter. You could make it be 5 million. The random number generator truly does run really quickly. There's a little bit of a delay, as you can feel it's a little bit slowing down, but you can see it really is starting to look like a flat line. That's the whole point. And when you generate enough data, it behaves exactly how it's supposed to. That's the whole point, that a random number generator, even though it's not really random, it behaves as if it is random. So that's what we have over here. Now, let's say you want to produce numbers. So these numbers, so I'm going to clear everything. By the way, there's a broomstick over here for the plots. And now it's empty. There's a broomstick over here. And here you can just delete everything. Now, RNG, maybe we could say PRNG, but I'll just say RNG. RNG, by default, produces numbers in the interval from 0 to 1. What if you want numbers in the interval from 1 to 3? Let's say you want to do it from 1 to 3. You want to change the interval. Then the way you would do it is, it's actually quite simple. You would write RUnif. So R means randomly generate uniform random variable. You will indicate how many numbers you want. And you can even see, now you cannot see it on my screen, but you should see it on your screen. There's a pop-up window that comes up that should show you the command, the way it goes. So you would generate 100 numbers, and then you write minimum is 1, maximum is 3. So that would be the interval that you're using. By default, if you do not specify the interval, by default it's always from 0 to 1, but you can change that. And now when you run, you can see the numbers fall outside the interval. Like that. Now another thing you can do, and this is interesting, is you can, there's of course a built-in command in the computer for automatically doing it. But let's say you did not have it, just for learning purposes. So you can only generate numbers from 0 to 1. So here's what you would do. you would generate 100 numbers from 0 to 1. But how do you make the numbers go from 1 to 2? You're just going to rescale them. That's all you're going to do. So the length of this interval is 1, and the length of this interval is 2. So you have to double the length. How do you double the length? You multiply by 2. So we're going to define y to be 2 times x. That will just mean you will multiply the number 2 across all of the numbers in the list. So this is a list of numbers. You just multiply 2 across all of the numbers in the list, and then you do plus 1. So 2x will produce numbers between 0 and 2, but you want them to go from 1 to 3, and then you add 1 to it. And by doing that, so when you do that, this is y, and now you can view, so let me do this from the very beginning, not to leave anything out. And now if you view what y is, you type over here y, you can see it generated for you numbers between 1 and 3. And you can check, is this truly uniform? Is this really uniform? So one way you can check is you can just do a histogram plot for y to see how it looks like. Maybe it's not very convincing, so let's make it be 100,000 numbers. Maybe this will be more convincing. And then we'll tell it to do hist y. Let's see if this convinces us that this is uniform. And now when I zoom out of the screen, you can really see that y takes on values between 1 and 3, and the bars are all fairly even, which indicates that this was generated in a uniform sort of way. It is an interesting question to ask, how do you prove this more carefully? So for that, I'll show you how you would justify that. So here's basically what we're saying. We're going to leave the coding world for a little bit. I just want to show you something. This is good for practice purposes. So this is what we're claiming. We're claiming that if a random variable follows the uniform distribution from 0 to 1, then if y is 2x plus 1, so this is a new random variable. So this is a random variable where you just, this is a random variable. So keep in mind, there's two different ways of thinking of x. On the level of a computer, x is just a list of numbers from that random experiment on the real line. Formally, x is a mapping from the sample space into R. We never even bothered to say what the sample space is. It's there, out there. It's an abstract sample space out there in the background. So 2x plus 1 would just mean it's the random variable where you take the sample point, you apply x to that sample point, that gives you a random number, you double it, and then you add 1. So there's like two different interpretations here of what we mean by a random variable, but more formally, that's what it would be. It would be a function on the sample space. And what are we claiming about y? We're then claiming that y will then follow the uniform distribution, but on the interval from 1 to 3. So the question here is, how do we justify this? How to justify this? I mean, it makes sense, but how do you justify it really as uniform? So this is the way we do this. Okay, so let fx of s be the function 1 if s is between 0 and 1, and 0 if otherwise. So fx, this is the PDF of x. That's the PDF function of x. We want to show that fy, the PDF function for y, that's the new random variable, and maybe for convenience, I'm not sure if I need it, but it's often a good habit to switch to a different letter, because sometimes when you substitute one for the other, it's helpful to sort of distinguish them. Of course, completely meaningless. You can always do it in terms of the same letter, of course, we know that, but I just find it convenient to switch to a different letter. That fy of t is going to be given by, and this is the part you have to be careful about, is going to be 1/2 if t is between 1 and 3, and 0 if otherwise. It's not 1, it's technically a half, because part of what it means to be a PDF is that when you integrate this, it has to be 1. This is 2 units across, so the rectangle has to be a ½ unit tall, so that the area underneath the curve, the PDF curve, has to be exactly 1. So this is what we want to show. Now we have to then go back to the interpretation. So let t be a number between 1 and 3. What does fy of t mean? What does that mean? So here's what it means. So here you have 1, here you have 3, and somewhere between 1 and 3 you have t. What it means is you're going to thicken this interval a little bit. So we're going to thicken it by epsilon, and so we have a point over here t plus epsilon, and we have a point over here, t minus epsilon. So if the epsilon is sufficiently small, you stay within the interval. It doesn't matter how close you get to these endpoints. If the epsilon is sufficiently small enough, this is going to work. This is an infinitesimal interval. And we're going to calculate the probability. So what we're asking is fy of t is approximately equal to, so this is calculating, this does not calculate the probability that you're equal to t. This rather calculates the probability that you, well, it's the probability, so it's, maybe I should just write it out first. You're going to calculate the probability that y lands inside that interval, right? So you're like, when you're dealing with absolutely continuous random variables, you never talk about the probability of landing at a real number. That always happens with probability 0. Rather, when you pick a real number, you thicken it by an infinitesimal interval, and then you ask, what's the probability of landing that this random variable, that this random number y lands somewhere in that interval? And what this is supposed to mean is that it has to be approximately equal to the PDF at that number multiplied by the length of the interval, the thickness of the interval. And as you make epsilon go down to 0, the more accurate this becomes. In fact, in a way, you're doing a derivative, because if you divide by 2 epsilon, that's like a derivative, right? You're dividing, you're calculating the change in one direction minus the change in the other direction, and then you're dividing out by the thickness of the interval, right? The change in the function, change in the variable, that's what a derivative is as you make epsilon go down to 0. So that's basically what you're doing. So let's calculate what this is. But what is y? Y is, by definition, it's 2x plus 1, right? That's what y is. That's how y was defined. And now let's solve for x. If you solve for x, then this is the probability. So you have to subtract 1. So this is t minus epsilon minus 1. And then you have to divide by 2, t plus epsilon minus 1. And then you divide everything by 2. So that is what you get. So what's the probability that you land inside, that x lands inside that interval? Now, because t was a number between 1 and 3, it means t minus 1 divided by 2 would be a number between 1 and 0. So basically, the picture here is whatever these numbers are that are between 0 and 1, and you have an interval over here that starts at t plus epsilon minus 1 over 2, and it ends at t minus epsilon minus 1 over 2. So those are the endpoints. And you're asking, what's the probability that you'll land somewhere in that interval? Well, but what do we know about x? X was assumed, and this is what we're assuming, it was assumed to follow the uniform distribution on that interval. So that means that the probability of landing in that interval only depends on the length of the interval and not the location of the interval. So it's just the length of the interval that matters. And what's the length of the interval? How do you find the length? It's where you start minus where you end. So you just subtract these two endpoints. So this is where you start minus where you end. And if we work out the math, what would that be? That the t's cancel. That's 2 epsilon plus 2 over 2. So we end up getting epsilon plus 1. Right, so t cancels with t, epsilon plus epsilon, 2 epsilon, negative 1 minus negative 1. Oh, that cancels, right? That also cancels. So we just have epsilon in the end. So this is just epsilon. So look at that. So what we've done this calculation, and we see that this probability is epsilon. So look at what we have. We have epsilon is approximately fy of t times 2 epsilon. So what does that tell us about what this is? So this one has to be equal to a half. So there you go. That one has to be equal to a half. And that is exactly what we've written over here. So as long as you stay on that interval, it has to be a half. And then you can analyze what happens when you're outside the interval, but that should be clear because when you're outside the interval, it's impossible for y to fall within those bounds. So that's how you would justify that more carefully. And while we're on this topic, I want to show you an interesting homework problem. So here's like a homework problem you can try doing. I'm going to do it on the computer, but I want you to try to figure this out yourself using some calculus. So suppose x follows the uniform distribution from 0 to 1. Find the PDF of y, where y is x squared. Now, before we do this on the computer to get an idea of what's going on, let's just understand that when you take a number from 0 to 1 and you square it, it becomes smaller. So if the PDF function for x looks like this, the PDF function for y, well, at the very maximum, y would still be 1 squared, and at the very minimum would be 0. So it will still be like sort of looks the same picture, but it will be more favored to be to the left. So you would guess that maybe it looks something like this. Well, we're not sure exactly what the curve is. So that's for you to figure out what is the correct curve here. But it has to be, is it a line? Does it go like this? So that's something for you to figure out how it looks like. But it has to be more favored to be smaller than bigger, because anytime you square a number between 0 and 1, the number gets smaller. So that should agree with our intuition. But just to show you, if we do this on the computer, just to show you what I mean, I'm going to clear everything all over again, and I'll generate x is going to be r unif, let's say 100,000 numbers. An easy way to write 100,000 is like this: 1e5. This means 1 to 10 to the power 5. That's the way 1e5, well, it just writes it like that, but it's interpreted as 10 to the power 5. So that's x, and then y is going to be x squared. All that means is that it's going to take every number that makes up x, and it will square those numbers. And you can then tell it to plot the density, the PDF density function of y. So let's do that. And now if we show this a little bit better, you actually notice that it's technically 0 over here. But because it's smoothing it out, it goes up. So in fact, what's going to happen is you have an asymptote. You will actually have an asymptote at 0. You have to work out the math, but you will have an asymptote, and it will be some kind of hyperbola, and it will just go down all the way down to 1. And then it does not actually move like this. It's 0 here. It's just smoothly transitions to 0. So that's what you're going to see. And for you, your exercise is to figure out what the actual function that represents this is, and then you can compare how close this simulation is to what you're supposed to get. You can even tell it to plot the curve on top of this to compare it. And this is where AI is very good. AI is very good at doing coding for you. It's pretty suspicious. It's not that great for doing math problems for you, but when it comes to coding, it's very good. So you can ask your favorite AI program to help you do some of the code. So if you generate this plot and you want to plot on top of this the PDF function to see if it matches with this simulation, you can ask the AI to tell you what the correct commands are, and then you just put them in there, and then you can compare whether or not you got the answer correctly. Okay, so this is how you can have a uniform random variable, but sometimes when we do random experiments, we want discrete random variables. Technically, these are discrete because you're using rational numbers, but how do you do coin flips, let's say? Because we're going to be talking about random walks. So how does one talk about coin flips? So here's what you do. If you type runif1, it will generate for you a number between 0 and 1 in a uniform way. So there's a 50% chance it's on the left, and there's a 50% chance it's on the right. So here's what you do. You would write less than 0.5. And you're asking the computer whether or not this relationship is true or false. So just to show you, if you write 0 less than 0.5, that's false. If you write 0.2 less than 0.5, that is true. So when you run the random number generator, it's going to pick a number for you, and each time it picks something different, as you can see. But if you highlight the whole thing, it will calculate the truth value for you. That's false. So you can interpret false and true as heads and tails. So that's tails, heads, heads, tails, heads, tails, heads, tails, and so on. That's what you can do. And if you know anything about writing loops, you can make this into a loop, generate a million of these. So that's what you can do. If you want to make an unfair coin that lands on heads 75% of the time, then you want true to occur 75% of the time. So you would just change this number. So you would make this be 0.75, and then you'll have more ones which are true, but some of them will still be false. So you can adjust it. But at 0.5, it's a fair coin flip. So this is the way you do coin flips. Now, of course, instead of using true and false, you can make the computer output 0 or 1. That's something you can do. But the good news is there's a built-in feature in the program that automatically does it for you, so you do not have to program it yourself. So here's the way it works. It's called sample. That's what it's sample. Sample just means, so sample, and when I type sample and I keep it like this, a pop-up window comes up that shows me how to use it. So the way this works is you have to type in a list of numbers. Now the way you type in a list, so let's say you want to type in a list 1, 2. If you type 1, 2, you're going to have a problem. And even if you put commas, you still have a problem. You have to put them in the list. The way you put them in the list is you use C. C stands for combine. So if you do C1, 2, then you've created a list where the first one is 1 and this is 2. You can, if you do C2, 1, that would be 2, 1. If you do C1, 1, so you want to create a list. So you create a list. So you create a list of heads and tails. So 0 and 1. That's normally the way we work with heads and tails. And if you're not sure how to use it, that this is just a helpful feature. I'm not sure how to use it. So I would just type over here $sample and click enter, and there is a help menu that comes up. It's called random samples and permutations. It says sample takes a sample of specified size of elements using either with or without replacement. So with or without replacement, if you've taken an undergraduate probability course, it means if something happens with replacement, it means you put the number in the list back and you try again and you do it again. So this is the way it goes. Sample XX is your list. So in this case, we have a list of 2 things. Size, how many times do you want to take things out of the list? So we say size is equal to 10. We want to take 10 numbers out of this list. Replace, do you want to replace it? Replace is equal to true. And now if you select, I'll get back to what this is afterwards, but if I was to run this, you can see heads and tails. Roughly half of them are heads and half of them are tails. In this case, we have 4 tails and 6 heads. If you do it again, so this is how you can do it. You can, of course, increase the number to 10,000, like that, 100, 10,000, whatever you want. If you put false, you're going to have an error because of the pigeonhole principle, that you only have 2 numbers. You pick one. If you run into this, just click escape. That's when you do not select everything. Just click escape. So if you do this, you're going to have an error, right? You cannot take a sample larger than the population. If you wrote, so like for example, if the list was 0, 1, 2, and you set size is equal to 2, you will take 2 numbers out of the list, but you always take something different. That's what that would mean. You're not putting it back into the list. But we want to put it back. So replace here is true. And we have 0 and 1. And now if you want to, so the point of the probability is to assign probabilities to these. So you would type, so if you want, let's say, heads to happen 66% of the time and tails to happen 33% of the time, you would just write prob, that sort of probability is equal to, so you could write, so you have to write another list, and you just have to match this list. So you can write it as 2 to 1. You can just write it like this. You can, it will rescale it properly. It just means this one is twice as common as that one. That's what it means. And then you can see, so let's say list is equal to 20, then you will see there's going to be more heads than tails now. If you make this be 1 to 99, then almost all of them will be, as you can see now, all of them are heads. But occasionally you do have a tail. It's just not very common. Most of them are just going to be ones. But as you keep on doing it, there it is, there's a tail, and you can, eventually you also have 2 of them in the same one. That is bound to happen at some point. It's just going to take a while. So anyway, that's the way that it works. So that's how you can do coin flips. That's how you can do coin flips. Now, the other thing I wanted to talk about is I want to talk about another list of random numbers that comes up a lot in probability theory. So let me remind you this. So we say, so recall, we say that x follows the normal distribution. This is normal 0, 1. And just to avoid confusion, this does not mean interval from 0 to 1. It means something else. It means that 0 is this is the expectation of x, and 1 is the standard deviation of x. That's what that's supposed to mean. So we talked about expectation and standard deviation. So there's a family of normal random variables. The one that we care about is normal 0, 1. That's the most important one because this is the one where the numbers are as simple as possible. And it's also because you can, just like you can very easily transform a uniform one on the interval from 0 to 1 by rescaling, you can transform any other normal into the normal of this type by properly rescaling it. So this is the one we normally, to use a pun, care about. And what is this? So recall, what does that mean? So it means that the PDF function, it's given by this function that we call lowercase phi of s, where phi of s is the following rather strange function that seems very ad hoc. It seems to come up out of nowhere, but we will rather explain where it comes from. But for now, we just accept what that function is. This is called the standard normal probability density function. The other normals, which are not the standard normal is of the type 0, 1, they have a more complicated function. So this is the one we prefer to use. Okay, so this is the one that is the famous curve that you see on the front cover of every probability book. It goes like this, like that. It happens to descend down very quickly because it's not just an exponential, but it's a square exponential. So that is what it means for a random variable to follow this. Now, when you do the random experiment on the computer, here's what you're going to see. This is the number 0. It will produce for you random numbers. Some of them will be positive, some of them will be negative, but most of them will be concentrated at the middle, and fewer of them will be further away. And there's no bound to how far you can be away. You can have like an extreme outlier all the way out there. There's no bound to how far you can be away. It's just these extreme outliers are very rare, and most of them will be down in the center. That's what it means. That's the reason why the PDF is shaped in this way. So if you want to get numbers generated in a normal way, then here is how you would do it. You would go back here. I'm going to clear everything all over again. I'm going to click on plots because we're going to draw some plots. So you do this by writing R norm. That's the way you write it. Instead of R unif, you write R norm. And then just like before, you just specify how many you want. I want 100. I want 100 numbers. And there you go. You can see some of them are positive, some of them are negative. And you can use different types of normals. The help menu will actually show you how to do that. The normal distribution, it shows you different functions here. You get to adjust the mean and standard deviation. These are the ones by default. That's the standard normal. If you want to have mean is 3, standard deviation is 5, that's the way you would do it. But by default, it's between 0 and 1. That's the one that we care about. And you can check, like, let's say we generate 100,000 numbers, and then we're going to tell it, let's call that x, and then we can tell it the plot density of x. Does it look the way it's supposed to look? Instead of being flat, like we've had it with the uniform, now you can see it actually is looking the way it's supposed to look. Okay, now you might wonder, and this is a good question to ask, how is the computer generating these numbers? And I'm just going to say this is not appropriate for our class. That's something you do in statistical computing. It's actually no different from the question of asking, how does a random number generator create for you numbers from the uniform distribution? It's sort of the exact same type of a question. But there's, of course, a way to do that. We're just going to accept the fact that you could do it. Now, I want to show you a very interesting example. So I'll go to the other screen, and I'll show you the example. We'll do the intuitive, we'll do the simulation, and then we'll work out the math. In this example, x and y will both be independent random variables that are uniform on the interval from 0 to 1. When we add them together, the question is, what is the new PDF function? Now, let's approach the problem in the following way. We're first going to solve it intuitively. Then we're going to do it with a simulation, so we get to see if our intuition is correct, and then we'll discuss the math behind it. It's an interesting problem. So let's understand what we're doing. We're taking a random number between 0 and 1, and we're taking another random number from 0 to 1. And the two numbers that are being chosen, they're being chosen independently of each other. And then whatever we get, we add up the two numbers. So at the very minimum, x is 0 and y is 0. So at the very minimum, this is 0. And at the very maximum, x is 1 and y is 1. So at the very maximum, you have 2. So this new PDF function, it should, so this is 0 and this is 2. And it should just be 0 over here. And it should be 0 over there, because those are just impossibilities. But what about when you're between 0 and 2? Well, let's say you take a number that's close to 0. Let's say you take 0 itself. Well, the only way they can add up to 0 is if x and y are 0 themselves. But and the same thing with the number 2. The only way you can add up to the number 2 is if x and y are both equal to 1. Whereas if you're in the middle, this is the number 1, then there's lots of ways to add up to the number 1. It could be 0, 1. It could be 1, 0. It could be a half. It can be 3/4 and a quarter, or it could be 1/4 and 3/4. So there's lots of ways to add up to a half. Now, to make this a little bit easier to understand, let's do an easier experiment with dice. So you have two dice, and one of them is red, one of them is blue, so you can tell them apart. And x, that's the number on the red one, and y is the number on the blue one. Now, x and y are uniformly distributed, but in a discrete way. Instead of on the interval from 1 to, so what's going to happen here is that x and y are going to be independent, because the two dice are independent of each other, of course. And this is going to be uniformly distributed, but in a discrete sense on the set of numbers from 1 to 6. So it's very similar to this, except these are absolutely continuous random variables, whereas these are discrete random variables. But it's the same idea, that x and y produce integer values in a uniform way from 1 to 6. They're all equally likely to happen. Now, when you add them together, so if you consider the sum, the minimum would be 2, and the maximum would be 12. But the only way you can get 2 is when you do 1 plus 1, and the only way you can get 12 is when you do 6 plus 6. If you take the number in the middle, which is 7, there's lots of ways to do it. You can do 1 plus 6, 2 plus 5, 3 plus 4, and so on. If you take 3, then there's two ways, 1 plus 2 and 2 plus 1. So as you can see, that as you move further to the endpoints, they become less likely to happen, and the number in the middle is the one that's most likely to happen. So based on this, you would guess that it has some kind of, it should be a symmetrical shape where it's higher peaked in the middle. And then the question becomes, what kind of a curve is this? Is it a semicircle? Is it a parabola? It's actually going to be a straight line. It's going to go like this. It's going to be a triangular distribution. And I have a notation that I made up. I've never seen anyone do this before, but it's, I think, nice notation. X and y is going to be distributed lambda, and by lambda I just mean the triangular distribution, because it looks like a triangle. It's the triangular distribution on the interval from 0 to 2. So that would mean, if you work this out carefully, that the probability density function for their sum would be, so it would be, as you can see, it goes, so what's, how high? It's 2 across. So in order for its area to be 1, it has to go up to 1. So this is a line with slope 1. So we would write this as, it's S, if S is between 0 and 1. What happens when S is between 1 and 2? Well, the slope is now -1, and it's shifted over by 2. So that would be 2 minus S. If S is between 1 and 2, we do not care what happens as S is equal to 1, because that happens with probability 0 whenever you have a continuous random variable. But you can see if you set s is equal to 1, this is 1, and this is also 1, so they happen to coincide right there. And it's going to be 0 if otherwise, 0 if otherwise. So that is going to be the PDF function. You can see it becomes more complicated, even though x and y have very simple to understand PDF functions. We can then check this using a computer, and then we'll explain how you do this using some calculus. Doing this on the computer, here's the way you would program this in, and you can do the random experiment yourself. You would write x is equal to r unif, and let's say we use 50,000 numbers. So this means 5 times 10 to the power 5. And y is r unif 5e5. Okay? It's important to write it like this, because if you were to write y is equal to x, what's going to happen is you're not using the random number generator to set the numbers for y. It will just reuse the same numbers again. So just to show you what I mean, if you were to run this, if you look at x, and I'm going to write head of x. I do not want to see all of the numbers. I just want to see the numbers that start off for x. So that's the way it starts off. And the head numbers for y are actually exactly the same, which is not a surprise because you're using x to generate the numbers for y. These are the same exact random variable. So you rather have to write this as r unif 5e5. Okay? So you're using a random number generator to fill up 50,000 numbers for x, and then 50,000 numbers for y. And part of a random number generator, as we said, a random number generator, technically a pseudo-random number generator, but it chooses numbers in a way that behave as if they were really independent. And so when you do it like this, by the way, if you just type in x, you have this mess of numbers, right? If you type y, you have this gigantic mess of numbers. You do not want to see all of them. So it's a good idea just to write head x, just to see the way the numbers start off, and then head y. And you can see in this case, the numbers go differently. Another thing I want to show you is if you were to type over here mean of x, this will calculate for you the expectation of x. The expectation. And the way it does it is it just takes all of these numbers, all 50,000 of them, and it just takes the average. Whereas the way we find expectation by integrating. So the expectation, the perfect expectation, is equal to a half. This one would not be perfectly a half because you have a finite amount of data. If you had an infinite amount of data, which a computer cannot handle, then of course you would have it be exactly equal to a half. This would be mean of y. You can see they're not exactly the same thing because the numbers that are being generated are not the same thing. And also, by the way, what happens if you multiply x with y? So if you were to take these two lists of numbers and multiply them together, this will be the random variable where you multiply x and y together. The mean of the product should be equal to the product of the means. It should be 0.25 because that's the property of that's a very important property for independent random variables, that the expectation of a product is the product of the expectations. So it should be 0.25. Also, the mean of their sum should be the sum of the means, as you can see. In fact, in this case, it's perfectly equal to the sum of the two numbers because you're just actually just adding them up. Okay, so that's just okay, now what do we want to do here? We want to look at the So you do not have to do this, but we can call z to be the sum of x and y. Okay, it's not required, but you can now take the sum of these two. And now if you look at the head of z, it will just add the two numbers, one for x and one for y. You can see at the very minimum, the number would be 0. And at the very maximum, the number would be 1. So some of these numbers are bigger, some of these numbers are smaller. And as you can see, most of them are actually somewhere in the middle. And now you can tell it to plot the density, the PDF for z. So you're going to take all of that data and you're going to use it to approximate the appropriate PDF function. And there's that triangle that you get, what we were talking about. Okay, that's how it works. Now I want to show you something interesting. Let's say so let me do it like this. Let's say this is x1, this is x2, this is x3. And we're going to take the sum, and z is going to be x1 plus x2 plus x3. You're going to add up. It's the same idea. What's going to happen? Well, at the very minimum, it would be 0, right? 0 plus 0 plus 0. And at the very maximum, it would be 3, 1 plus 1 plus 1. But it will no longer be triangular. It would actually be parabolic. It will be pieces of parabolas together. I'm going to show you how you can do this. It is actually very tedious to work out the calculus because there's so many different cases to consider. But just to show you, as you can see, it has a bit more of a bend to it. A bit more of a bend. And you can keep on going. You can do x4, 5e5, and just add it over here and do this random experiment. And it starts to look like this. And now when you start to look at these numbers, that starts to be a little bit suspicious. That looks like that normal curve that we talked about, which we're calling by phi. And it is, except there's one problem over here. This is not the curve that's centered at 0. It's a different type of normal. So you can convert it back to, yeah, you have to readjust it. So that you have to sort of rescale it a little bit. And the way you would do it is you would subtract the number 2 from it, because 2 is the center, so you subtract 2 away. And then you have to divide out by the spread. I think the spread should be 2. You'll see the reason for this later on, by the way. So if you're not sure why I'm doing this, but I think if I do it like this, then that is actually the normal curve that we're used to. It's centered at 0, and it spreads out the appropriate amount. So those are some simulations. Let's explain what happens. Let me just quickly explain how that curve looked like. So this was the triangular distribution, but if you have 3 of them, for people who are curious, I'll just tell you what the answer is. You'll be able to check this yourself if you really want to, but as you will see, it's a little bit tedious to work this out. So when you have 3 of them, this is what's going to happen. You have 1, 2, so you have 1, 2, 3. So the way, so you have 1 and 3, then you have the number in the middle. So this is how it goes. It's parabolic up to the midpoint, like this. So that's like a piece of a parabola. And then you have another piece of the parabola right over here. So these are parabolas. They're not full parabolas, they're pieces of parabolas. And when you put them together, that's how it starts to look like. That's not a normal curve, because the normal curve is not given by parabolas. It's given by a squared exponential. Or maybe I should say better, an exponential of a square. But it starts to resemble that curve that we're familiar with. But anyway, for the people who are curious, let me explain to you how you would solve this problem. So this is an interesting solution, and it's going to use something called convolution. Definition: let f and g be functions on the real line, be 2 functions. We define a new function, f convolution g. And this is a function that will go from the real line to the real line. So this is an operation on functions. Functions are more flexible than numbers. You can do more things with functions than you can do with numbers. Like, for example, you could talk about the composition of 2 functions. That's something that does not make sense for numbers. But here there's this new operation. If you've never seen it before, this is called convolution. So, and how is it defined? So here's the way it's defined. So convolution is I have to tell you what you do to a number. Let's say that number is x, or whatever you want to call it. Here's the way you do it. So this is the definition of convolution. You're going to integrate from negative infinity to infinity. And you're going to do it like this. This is f, this is g. You're going to write f of y. And here you're going to write x minus y. And then you do dy. So what we need to understand is that x is being held fixed, and it's the y that's being integrated. By the way, it's not difficult to show this. I'm not going to do it. It's not difficult to show this, but this operation is actually commutative. So it would be the same thing as writing g of y over here and then writing x minus y over there. The important part of this procedure that you need to understand is whatever you put in for x and y, they have to add up. They have to add up to x. So as you can see, these 2 quantities, they add up to x. So the x is being held fixed, the y is the running variable, and it's done in such a way that these add up to x. That's called convolution. Of course, assuming, right, so of course, the convolution of 2 functions might not exist after all, because you are doing integrations. And because it's an improper integral from negative infinity to infinity, of course, things might blow up and convolutions may not exist. However, when you're dealing with probability density function, the convolution always exists. If f and g are probability density functions, in other words, what does it mean to be a probability density function? It means that f and g are non-negative, and they happen to integrate. I'll just write it like this. F with respect to the Lebesgue measure is 1, and g with respect to measure is 1. So that's what we call probability density functions. If they happen to be probability density functions, then convolution will always exist. Convolution will exist. When I say exist, I just mean that the integral comes out to be a finite number. And it will be a probability density function itself. That's the other. It will be a probability density function itself. It requires a proof, of course, but I do not feel like going there. I just want to tell you what the answer is so you get to see it. I'm not sure if we'll ever even use this. It's just something interesting to think about. And, okay, so how do you find the probability density function of the sum? So here's a proposition. So if x and y are independent, absolutely continuous, random variables, then x plus y is also an absolutely continuous random variable, and its PDF function, make up a letter, let's say S, it's going to be the convolution of those two at S. So that's the way you do it. And I'm going to demonstrate this calculation in the example that we did when x and y are uniformly distributed. Okay, so this is what we have. This requires a proof, but I'm going to give you an explanation that will hopefully make it convincing for you. And the explanation that I'm about to give you, that's basically the proof without any of the mathematical formalism behind it. The idea is this. You have two random variables, and you want them to add up to S, right? X and y add up to S. Well, if the sum of two random variables add up to a number S, how can that happen? Well, that would mean one of them can be anything you want. Let's call it t. And then the other one is forced to be S minus t, because that's the only way they can add up to S. But that's starting to be a little bit suspicious. That looks like convolution. And that's exactly what you're doing. You're going to do fx at t. You're going to calculate the PDF of x at t. You're going to multiply it because of independence. This is where independence comes in. You multiply with independence with the other one. So this is fy s minus t. And then you sum up all of those possibilities. So that's where integration jumps in. So then you sum up all of them. Okay, and here we have to understand that x is fixed. That was the chosen s at the start, whereas t varies over all of these possibilities. So you're integrating with respect to t. But that's exactly what convolution is. That's exactly the convolution operation. In fact, I would say that the solution to this problem is how convolution came up in the first place. It's not like one day some mathematician decided to make up this unusual operation on functions, but there was a problem that led to it. And a convolution is a type of averaging. It's like a weighted averaging. So if you want to give a very simplistic explanation to what a convolution is, it's a weighted average where you're summing up values of one function, and then you're using the other function as sort of weighing how much each one has an impact on the sum. And if you're willing to accept this, I think it's fairly believable. You can turn this into like a more rigorous proof to show that this works out. But if you're willing to accept this, let's do the calculation that we had. So the calculation that we had was x and y were both uniformly distributed on this interval, and they were independent. And by the way, I want you to notice something. I've said this so many times, but this is so important, that notice that in all of these propositions and all of these computations, we're not going back to the sample space. You see, we normally work on the real line. The sample space is there. It's a necessity for theory that justifies many of the things that we say. But the calculations are done using the real numbers, and that's where the calculus comes in. So how do we then find? So fx plus y, this is the probability density function of their sum at a number s, would then be equal to the convolution of those two functions. It does not matter in what order you do it at s. And how do we do convolution? Well, the way we do convolution is we integrate from negative infinity to infinity fx of t, fy, ts minus t dt. But fx of, let's say, u is equal to, so what's the PDF for x? It's the function that's 1 if u is between 0 and 1, and 0 if otherwise. And by the way, that's also the PDF function for y. So x and y, their distributions are the same. The random variables are different, but their distributions are the same. And this is their PDF functions. They have the same PDF function. It's 1 when u is on that interval and 0 otherwise. So focus for now on this piece. We're integrating over t. But as t goes from negative infinity to infinity, this will be equal to 0 unless t is between 0 and 1. So this integral, even though it looks like an improper integral, it can be rewritten as a finite integral from 0 to 1. And then this is just 1, right? You just replace that by 1. And so we're left with fy s minus t dt. Now it's going to be convenient to do a substitution. Let's call this u. U is s minus t. Okay, that's going to be u. Keep in mind that s is fixed in the problem and we're integrating with respect to t. So that would mean that du is negative dt. S is a constant. It's treated as a constant. So this will become fy of u. Dt will become du with a negative sign. And now we have limits of integration. So t was 0, t was 1, and now we have limits on u after doing the change of variable. If t is equal to 0, then u is equal to s. And this would be s minus 1. So there we go. That's what we get. And then we can absorb the negative sign into the integral. And we have to calculate the integral from s minus 1 to s fy of u du. Now, it would be very helpful to draw the picture of this PDF function. So the PDF function that we're integrating, it is 0 over here. This is 1. And it's 0 over here. And it's equal to 1 over here. And this s, so we're integrating from s minus 1 to s. So now we just have to consider where s is located. If s minus 1 is all the way out here, s minus 1, and this is s, then we're integrating over 0. So then we have a bunch of cases. This is going to be 0 if s minus 1 is greater than 1, which is another way of saying s is bigger than 2. Likewise, if s was to the left, if s was over here, s minus 1 would be there, and then we're integrating over, we're just integrating 0. So it would be 0 if s was less than 0. And then it's the intermediate cases that are a lot more interesting. So what's more interesting is when s minus 1 is on the left and s is in the middle. So if s is over here and s minus 1 is over there, so when we integrate, this is the only piece that actually contributes area. And so we have a rectangle that's s across and 1 unit up. So in that case, we get s if s is greater. So in this case, you can see what happens. S minus 1 is negative. So that means s has to be smaller than 1, but s has to be positive. And then you can figure out the last case. So the last case would then, I'm not going to write it out, but you can do it yourself. And then the last case would be where, this is the last remaining case, is when s is over here on the right, and here you have s minus 1, and then you end up calculating that area. And you can figure out what that is, and that would be 2 minus s, as we mentioned before. because basically you do 1 minus that, you find the length, and that's how you get 2 minus s. As you can see, this calculus procedure, it's a bit annoying because you do have to consider cases, and when you have to consider a lot of cases, problems become tedious. So if you really wanted to, you can try to figure out what happens when x1, x2, x3 are all independent and they follow the uniform distribution from 0 to 1. You can try to figure out the probability density function for what their sum is. It's going to be tedious because there's a lot of cases to then think about, but basically the way you would do it is you do it 2 steps at a time. You can group them in parentheses like this. So you would say it's the PDF function that we just found, convolution with x3. So you have to take the function that we just found, that piecewise function that has 4 separate conditions, and then you have to take a convolution with this one that has 3 separate conditions, and then when you put them together, you have many other separate conditions. And you can work it out, and because you're integrating, the degree goes up. So that should suggest why you go from something that's flat, right? Something that's flat, which is a polynomial of degree 0, to a line, which is a polynomial of degree 1. And if you were to integrate again, the line will integrate to something of degree 2, and that's how you end up getting that parabola shape. So that's what it has to do with. And with this, we're going to conclude with this lecture. Okay. So in the next lecture, we're going to introduce random walks. We're going to show that random walks, we're going to define what a random walk is rigorously. We're going to show that it exists. And we're going to also show computer simulation, some properties and things like that. And from that point on, hopefully the course will become more interesting if all of this theory was not as fun. But maybe the computer simulation stuff that we did today, maybe you found that to be more exciting. And that's what the course will be. It'll be a blend of different stuff, theoretical stuff, some application-driven stuff, some computer simulation stuff, so people can get something out of the course depending on what kind of interest you have.